So we've built the theory behind variation of parameters. Let's see it in practice. So let's take an example. We want to solve this differential equation here. Now notice this does not fit in the form of the undetermined coefficients method. Okay, so that wouldn't work. We got to do something different. And we're going to use the variation of parameters. So we'll go slow for the first example and go step by step. So we put the differential equation in standard form by dividing by A2 there. And we get this, okay? And this yields the P and Q for our differential equation according to the form up here, okay? And here goes our f of x. Step 2, we find the complementary function. And so we look at the associated homogeneous equation and we get the general solution for that, and that's what's called the complementary function. Now here we have the associated homogeneous equation is just a differential equation with constant coefficients, so we're not going to have a problem. We take a look at the auxiliary equation, we get the roots, we get complex conjugate roots. We identify the roots with alpha equal to 0 and beta equal to 3. And so here goes our complementary function. Of course, we have videos for the method of undetermined coefficients and for solving homogeneous equations. So one could review that if this step is unclear. Step 3, compute the Wronskian, W1 and W2. So the Wronskian of Y1 and Y2, okay, which we identify here, is the determinant of this, okay? And if this is y1, this is its derivative, this is y2, its derivative. And we then take the determinant of that, we get this over here, cosine squared 3x plus sine squared 3x is 1. And so we just have 3 times 1 there. W2 has the second column substituted for this. And plugging this in, we get this right here. W1, similarly, we would get negative 1/4. And so we've computed these. Step 4, we want to compute U1 and U2. It's a good idea to go back to the formula here for U1 and U2. Okay, no need to rederive it. So just straightforward application of the formula here with W1 up here and W here. We integrate, okay, and we get this. And this integral is with respect to like dt, just a dummy variable. And you could think about it as an x up here, okay? Now someone might say, well, why don't you add a plus c there for u1? You can, but it turns out to be useless because that c could be absorbed into the complementary. So if you had u1 plus some constant, and you also have this term from the complementary function, well, you could just absorb that c, the constant of integration, into the complementary function c. So no need to do that. U2 then, integrated, we use the method of substitution for integration. Here we use v. It's common to use u, but that's taken. So we use v, where v is going to be sine 3, 2. Okay? And we integrate. So we'll do the substitution and integrate that. So you know, dv here is going to be equal to 3 cosine 3, 2. Okay, so that gets absorbed there. That's where that 1/3 comes from. And we're substitute back. You get 136 natural log sine 3x. So that was step 4. Step 5, we form the particular solution. The particular solution is by assumption of this method, u1 y1 plus u2 y2. Well, here goes our u1. We multiply it by y1. And here goes our u2, we multiply it by y2. And so we got our particular solution. Now what's the general solution? The general solution is going to be the complementary function plus a particular solution. And so here it is. And we just solved the problem that we couldn't have done with the method of undetermined coefficients, but the method of variation of parameters worked. This final step is just a placeholder. If we had a initial value problem or boundary value problem, we would then take this general solution and apply the initial conditions or boundary conditions on the general solution, okay, not just on the complementary, but on the general solution to fix the constants. All right, so let's look at another example, and this time we'll go quicker. So we want to solve this differential equation. Notice here that this would not work with the method of undetermined coefficients, this 1 over x. Doesn't follow that polynomial, exponential, sine, cosine products and finite products and sums of those. First we get the complementary function. We look at the associated homogeneous equation. So here's our auxiliary equation to that. Here are the two roots, so we get two distinct roots, and we identify y1 and y2. We compute the Wronskian of these two, and we get -2. We compute w1 and w2, and we get what you see here. And of course, all of these formulas are above. We're moving quicker for this example. And we have the formula for u1. We integrate. Something to recognize right off the bat here is that this integral cannot be computed in terms of elementary functions. Okay, we cannot write it in terms of the standard elementary functions that we have. It's called a non-elementary function, and it's actually an integral defined function. So we're going to leave it as just an integral. Okay, and so we're integrating to x, and we just leave it. So the particular solution is u1 times y1, and so here goes our y1, okay, and here goes our u1 there, which includes that 1/2, and likewise here, and we're just going to leave it like that as an integral defined function, okay. So our general solution is the complementary function plus y particular with the integral defined function. Here he writes non-elementary integral, thus we leave the integral defined. Leave it as an integral defined function, which is fine, okay. If we were computing this for specific values, then we could apply this the specific values to this function and compute actual numbers. Okay, so if we had like a IVP and we were looking for a specific point, we could compute these numerically.